Hello everyone, I'm Jonathan Messias. I'm a second year PhD student at the Max Planck Institute for Software Systems here in Germany, and I'm also a student at the Universität des Saarlandes, also in Germany. Today I'm going to give a talk on my current work on blockchains commit times, an analysis of how miners choose Bitcoin transactions. This is a joint work with Mohammed Al-Zayat from MPI SWS as well, with also Balakrishna Chandrasekaran from MPI Informatics, and also with my advisor Krishna Gumadi from MPI SWS as well. So as of right now, there are more than 50 real world use cases for blockchain. So blockchains are quite important, right? We know cryptocurrencies like Ethereum and Bitcoin. We also have other applications like land registry for some healthcare as well, applications on supply chain, more regarding distributed applications, some of them running on top of Ethereum as well. And also there are some applications, for instance, for donations as well, where you can use blockchains to track your money, whether the money that you donate is really being used in what you expect, right? But for this work, my focus will be on Bitcoin only, okay? But before I start, I'd like to introduce the top two blockchains, as we already know, Bitcoin and Ethereum. So, for instance, in these plots, we can see the trend that the number of blocks generation, it's basically linear, right? On Bitcoin, usually we have a new block included through the blockchain on average every 10 minutes. On the other hand, in Ethereum, it happens around 15 to 17 seconds you have in a block. So this explains why the block generation over time in a cumulative way, it's basically linear. But when we also observe the red line, it's basically the number of transactions issued over time for both of the top two blockchains. We can clearly see that for Bitcoin, around 60% of all transactions ever issued were included. I mean, in the last 2.5 years, which is a lot. And also, when we look at Ethereum, it corresponds to 80% of all transactions included in just 1.5 years. So clearly, the number of transactions is increasing really high. And all of a sudden, maybe we will not have enough blocks to accommodate all those transactions, let's say in 10 years, who knows? So could this become a problem in the long term, let's say 10 to 15 years? Will all transactions be included eventually into the blockchain? So we want to analyze this kind of transaction ordering and inclusion as well. As of right now, there is a common wisdom. People usually believe that transactions are being prioritized based on fee per byte. So essentially, they believe that miners rank those transactions based on the transaction fee. By transaction fees is each user offers some fee to incentivize miners to include their transactions, divided by their transaction size in bytes. But there is no guarantee that this common wisdom is being followed, right? And so we want to investigate whether miners are fair in the transaction order. Are they really following this strategy or not? Which are the policies that they are following, right? So yeah, we want to investigate how miners actually order those transactions. But before I start talking about that, I want to introduce how transactions are selected. At least in Bitcoin, every new transaction that miners get to know, they are stored in a special memory cache, which we call mempool in Bitcoin. So mempool contains all those transactions that are waiting to get included, right? And it's up to the miners to select from the set of transactions in the mempool, which are the ones that they want to include in their own block. And so once they validated their block via the crypto puzzle that they have to solve, right? So they push their block into the peer-to-peer network, and hopefully the block will be accepted and all those transactions will be set as confirmed. Miners, they also get some incentives to mine blocks. For instance, they get a block reward, which basically has every 4 years, or more precisely, every 210,000 blocks in Bitcoin. So as of May, it was, I think, 12.5, and now is 6.25 Bitcoins that every miners get when they mine a new block, plus transaction fees. So as I said, every users, they also include some fees on their transactions, and so miners, they get all transactions fees that they decide to include. Eventually, this block reward will become zero. So miners will not get any incentive for mining blocks apart from the transaction fees. So fees on the future will be, at least unless they change the protocol, will be the main incentive for mining. But what do transactions look like? What are the characteristics of transactions? So essentially, we deploy, in order to have that data to make analysis, we deploy a full node Bitcoin um, here at NPI, and we also gather the data from Mempool in order to study the miners' policies. So this dataset comprehends two parents. For instance, the dataset which we call A, it basically corresponds to February, and dataset B, the whole month of June. So we have the number of transactions committed, number of blocks, and also the number of empty blocks. By empty blocks, I mean it's up to the miner to select which transaction they want to include, right? But they can also decide to not include any transaction at all. So we call those blocks like empty block, which means blocks that miners decide to not select any transaction at all. Here we have the plot that shows the mempool usage over time for both dataset. As we can see, for instance, the block has a limit size, and miners, they can decide to include up to 1 megabyte of transactions. And so essentially, when we look at those plots, we can see for dataset A there, or in the middle, for example, around March 1st, it would require more than 16 blocks to clean the mempool, right? And on the other hand, for dataset B, there was a period around 25 and June 25 and 30 that it would require more than 50 blocks to clean the mempool, which means that there were a lot of transactions waiting to get included. And there is also this fear of every going commit time. So once you issue the new transaction, when your transaction will be actually included, right? So we made some analysis on that. And we see for both data sets, for instance, dataset A, the majority time that the transaction has to wait, it was 1 day. But for dataset B, some transactions got, let's say, included in more than 2 days and also 5 days. So transaction times varies a lot, as we can see. But the majority of them are being included, let's say 60% or 50%, 60% of them are included right in the next block. But even though there are some transactions that are starving or waiting longer. And when we see the distribution of mempool size over time, we can see that in the green line in the right plot, so we can see the block limit, which is 1 megabyte virtual size. And essentially the mempool is really congested. For instance, mempool is congested at least 75% for dataset A and 92% of dataset B. When we look at these plots, we can see that Mempool is highly congested, which means that there is more transaction waiting to get included than the next block would be able to include. So you have a competition among those transactions, right? But do people pay more when there is a congestion? One thing that we noticed is it's yes. So basically, users they offer more transaction fee when when the Mempool is congested. As we can see, when Mempool is highly congested, or I mean, it's has more than 4 megabytes of transactions. So basically, users tends to offer more transaction fee I mean, hopefully to get their transaction included faster. And in dataset B, I mean, the highly congested Mempool, we can clearly see that users offer more. I mean, to expect that their transaction to be included early on. Also, we can see that based on those plots that once you offer really high transaction fee, your transaction get included really faster, right in the next block, for instance. However, even though that depend on the Mempool configuration, there will be some even highly Feerate transactions that also wait longer to get included. But when you offer less, of course, your transaction get longer. Somehow it demonstrates that miners tends to follow the fee-per-byte strategy, but not purely. So we want to take a look on that. So in order to do that, so do miners follow the common wisdom? So in order to do that, we had to establish a baseline. So basically, we gather all transactions in our Mempool. I mean, that miners actually they had the option to include as well, and we ranked those transactions, we ordered them based on fee-per-byte. So if miners they follow 100% of the time the fee-per-byte strategy, so we would expect something like 100% intersection between the actual transaction order that miners select, which we call B miner, and with our baseline, okay? Remember that our baseline contains all transactions that were in our Mempool sorted based on fee-per-byte only. But do miners really follow this strategy? So actually, one thing that we noticed is there will be 3 options. Miners can follow those fee-per-byte strategy, and so we have intersection, but miners can also decide to include some transactions that we didn't. So basically miners decide to prioritize some transactions, right? But they can also ignore some transactions. By ignore, I mean, we decide to include based on fee-per-byte, but they decide to not include. But it's a distributed system, right? And the nature of distributed systems, we cannot make any guarantees whether miners have the same set of transactions that we have. So we give miners the benefit of doubt in this specific case. So in order to do that, we rank all those, we checked all those transactions that we had an intersection, and we found out that in the median, 78% of all transactions, actually miners, we used the fee-per-byte strategy. So we had an intersection. So also the top 5 mining pools at that time, they also have similar pattern here. So it suggests maybe miners are using are actually following the fee-per-byte strategy, but with some variation, and we want to understand why. So one thing that we also did is, okay, so due to the nature of the distributed systems, what would happen if we as we gave the miners the benefit of doubt, what would happen if we include some cutoff? For instance, 1 minute, 10 minutes, 1 block, 2 blocks, and so on. So we can see here in this plot that basically it contains all transactions that we decided to include and miners didn't. And of course, it's a distributed system, and so we decide to include those cutoffs, and even with 1 or 2 blocks cutoff. By this I mean, okay, let me only consider transactions that we got at least 1 or 2 blocks before, 1 minute, 2 minutes, or 10 minutes before, right? And even though miners decide to not include those transactions, miners ignore those transactions. So why is that happening, right? Um, and this is really strange, right? And it's not the case that miners, they got those transactions later. Basically, they decide to not include them at all. And so do miners use a different protocol? Of course, if they are not using fee-per-byte purely strategy, what are they using, right? And so there are some, in this plot, we show that the transactions that miners decided to include and we didn't. I mean, those transactions that are not following the fee-per-byte strategy. So basically, those transactions offered less fee per byte. And so it means that there were transactions with higher, that gave higher incentive for miners to include them, but even though they decide to not include. So what is going on? Are miners simply ignoring those transactions and prioritize others? Why? And so maybe perhaps miners are using a different protocol, a different sorting algorithm, or even though maybe they are providing some other services like transaction accelerators. There are some mining pool grids that they actually offer these servers where people can pay off-chain to accelerate their transactions, let's say via another cryptocurrency or even a credit card. So it's not transparent, right? And one thing that we realize is that miners really deviate somehow. They somehow deviate from the strategy. Maybe they are using another strategy. Maybe they are using a combination of fee-per-byte strategy and another strategy, right? We want to know better this kind of thing, right? And the conclusion of this work is the following. fee-per-byte only cannot explain the dequeuing policy of miners. So users cannot purely trust or rely on this metric only to offer their fee. Maybe they will offer higher fee rate than they should, and their transaction will get, included later on. And mining pool, the top mining pools also, they have almost the same behavior, and they do not make their their rank ordering transparent. The way that they selected transaction is not transparent at all. And come on, we keep saying that the beautiful of a blockchain is safety, security, right, and also transparency. But should miners and mining pool grids also provide transparency in the way they prioritize transactions? So, and if yes, what's the implications for that? So why do miners deviate? It could be due to also the Stratum protocol. Maybe they want to decrease the overhead of the network, and so they decide to send different sets of transactions to different miners, workers, right? And we couldn't check that, but it's a good kind of question that we plan to answer in the future. Also it could be also due to the transaction accelerator services, as I told to you before. And as a future work, we want to apply our methodology to other cryptocurrencies as well and other blockchains. So is that the case that this behavior is also happening in Ethereum? And what would be the consequence for the central digital banking currency, right? The CDBC. And so, yeah. And finally, we also want to build a transaction predictor where we could somehow help users to estimate the proper fee that they should offer to get their transaction included. So yeah, that's it for today. Thank you so much for attending this talk. If you want, I'm open for questions, and please feel free to drop me a line via email or also via my social network. And you can find all information on my webpage as well.